Welcome. My name is Mats Gustafsson, and I present the paper Degrees of Freedom for Radiating Systems. So the number of degrees of freedom is a fundamental concept in communication, antenna design, and inverse scattering. We show that the asymptotic number of degrees of freedom of a region is governed by its shadow area expressed in wavelengths. A general theory is developed for arbitrary-shaped regions with a focus on far-field radiation, but also extended to include communication between regions. The results unify and generalize earlier findings for canonical geometries, and it's also consistent with Weyls' law. The theoretical results here provide physical insights that complements numerical simulations. So the number of degrees of freedom can be viewed from many different perspectives. Starting with applications, we can ask many questions. For example, in this paper, we really focus here on what is the number of degrees of freedom in communication channels for in MIMO. How many channels can we get? But as you can see, there are many other ones here for number of antenna ports we can have, even down to thermal radiation. All of those involves degrees of freedom. So what is analyzed in all of these systems is that you look at the eigenvalues because it determines how many parameters you have. And somewhere you find kind of a corner in these cases. And this is where it breaks up and starts to be expensive to use more parameters. So in this case, you can see you have around 100, and that is the number we would like to determine. If you do the same size and you look at the parameters as a function of size, you can see for small ones, you have a low numbers, the number of dipoles. For larger cases, this asymptotic reading kicks in, which are these dotted lines here, which is the one I'm talking about in this presentation. It has a very long history of looking at degrees of freedom. It goes back more than 100 years ago. Work a while, later Shannon, and many other people, as you can see down here. So it's a very well-researched topic. Many types of geometries have been considered. For example, cases where we can do analytical solutions and we can actually calculate the eigenvalues. In this presentation, I focus more on arbitrary-shaped regions, either radiating to the far field or between regions. So looking now at what we've done in the paper, and that we show that really this number of degrees of freedom that we have for these cases, this is what I showed as NA here. And when that is large, it scales with the shadow area, which is this A that I have here, just measured in wavelengths. So if we know the shadow area, we can determine the asymptotic number of degrees of freedom, when that means we understand what are these degrees of freedom we can get. What is shadow? If you have an object here, you all know what the shadow is. Now we need to determine the area of that shadow. And we do that by illuminating it from all directions and summing up what these are. This is basically what we need to compute. That is easy to compute. So let's look at what's happening if we do that for some cases. Here are now 6 different regions. And what is plotted on the horizontal axis here is the eigenvalue index n normalized with this asymptotic value NA determined from the shadow. And you can see that it starts to break off around this point 1. So it seems to be consistent with what we do. If we look at the communication between two regions, and of course the channel is computed numerically here, but again, we can see here it breaks up at 1, and that is what is done basically analytically to determine the NA, and that is the one that we have here. If we look at the number of significant characteristic modes, you can calculate characteristic modes, but you can also calculate the shadow area. You get these dashed lines. And you can see that it actually represents approximately how many significant characteristic modes to have. So what we've done in the paper is really to generalize and unify many other results. It provides physical insights to this very fundamental problem and gives us understanding. And you can read much more about it in these papers that we have down here. So with that, I thank you for your attention.